You ever have that feeling you're talking to an AI with amnesia? You give it a document, you ask a question, and then the next day you have to upload the exact same document all over again. It feels like we're constantly teaching it the same things. So, is it ever really learning? Is any of that knowledge sticking around? Let's get into it.
Andrej Karpathy, one of the brilliant minds from OpenAI, absolutely nailed the problem with this quote. He's saying that the standard way we do this, a method called Retrieval Augmented Generation, or RAG, is basically stuck on a treadmill. It's just rediscovering knowledge from scratch every single time. Nothing accumulates.
So that begs the question, right? What's the alternative? What if, instead of hitting the reset button on every single query, your AI could build a knowledge base that actually grows? One that gets smarter and more connected the more you feed it.
Okay, so before we get to the really elegant solution, we have to properly understand the problem. And the problem is RAG. I mean, it works, but it's just fundamentally inefficient. It's like asking your AI to rummage through a massive, messy library for every single question you ask.
This slide really lays it out perfectly. Think of RAG as a scavenger hunt. Every time you ask a question, it has to frantically search through all your raw, messy files to find little bits and pieces that might be the answer. But the LLM wiki idea, that's more like a patient librarian. It reads a document once, figures out the important stuff, and neatly files it away in a structured, growing knowledge base. It's not repetitive, it's cumulative.
And this brings us to Karpathy's big idea. He suggests we need a paradigm shift. We should stop thinking about the LLM as just a fancy search engine and start thinking of it as something much more powerful, a compiler.
And this compiler analogy is just perfect. All your messy stuff, your PDFs, your articles, your random notes, that's your source code. It's clunky, it's repetitive. The LLM then acts as the compiler. It processes all that raw material, cleans it up, and turns it into a sleek, efficient executable. And in this case, that executable is your own personal wiki.
And here's how it works in practice, and it's so simple. Step 1, you just dump all your messy files into a source folder. Step 2, the LLM gets to work. It reads everything, pulls out the key info, and connects the dots. And then, step 3, it spits out these beautiful, clean, interlinked Markdown files into a totally separate wiki folder. That's it. That's your new knowledge base.
And maybe the best part is just how simple this is. Look at this folder structure. There's no complicated vector database, no server you have to spin up. It's just text files. One folder for the messy input and one folder for the clean AI-generated output. That's all.
Okay, so we've seen the what, this whole compiler idea. But to really get why it's such a game changer, we have to pivot. We need to peel back another layer of the onion and get into the really deep, weird stuff, which is how these models actually see the text we give them.
And you might be asking, okay, but why is this so much better? Why go through the trouble of compiling everything if the LLM can just read the original files? And that is the perfect question, because the answer is where things get really, really strange.
And here's Karpathy himself, pointing us right to the culprit. The secret isn't in the fancy neural network, it's in a step that happens before all of that, called tokenization. And listen to his words, hairy, gnarly, hidden foot guns. That should tell you everything you need to know. This is where the magic and the madness happens.
Welcome to the hidden world of tokens. Before an LLM even sees a word, our language gets shattered into these little fragments called tokens. They are the only thing the model actually processes, and honestly, they make no sense from a human perspective.
This is just wild. Take a super simple word like egg. As you can see here, depending on whether it has a space in front of it or if it's capitalized, the LLM might see it as one piece or two totally different pieces. The model literally has to learn from scratch that all these different combinations mean the same thing.
And it gets weirder. Numbers aren't safe either. Look at the number 804. A common tokenizer breaks that into two separate pieces, 80 and 4. The LLM never actually sees the number 804. It sees two unrelated tokens and has to figure out that they belong together. It's no wonder these things can struggle with basic arithmetic.
This even impacts something like computer code. Older models like GPT-2 treated every single space in Python code as its own separate token. Think about how bloated and inefficient that is. Newer models like GPT-4 got way smarter, grouping 4 spaces into a single token, and that change alone was a huge reason for its massive leap in coding abilities.
So all of these little quirks, these foot guns, as Karpathy calls them,
They're the source of so much of the weirdness we see in LLMs. It's why they can struggle with simple spelling, why they're often worse at non-English languages, and yeah, it's even how you get bizarre security holes like the solid gold Magikarp issue, where one specific string of text could crash a model just because of how it was tokenized.
Okay, so let's bring it all home. How does this super low-level, weird token stuff connect back to our high-level wiki idea? Well, this is where it all finally clicks into place.
And here's the payoff. When you use a standard RAG system, you are feeding the LLM a messy, inconsistent, and totally unpredictable stream of tokens every single time. It has to deal with all that hairy, gnarly weirdness on every single query. But with the compiled wiki, all that text has already been processed into a clean, consistent format. The weirdness is handled once, up front, during compilation.
So that's really the heart of it. The LLM wiki pattern isn't just about organizing information for us humans. It's about pre-processing messy reality into a clean language that the AI can understand reliably and efficiently. You're cleaning up the signal before the model even sees it.
You know, when you go this deep into how these things work, you start to realize that the real innovation in AI doesn't always happen on the shiny surface. It happens down here, in the messy, fundamental, and often hidden mechanics that make everything run.
And Karpathy isn't joking about this. He says that eternal glory is waiting for whoever can finally get rid of tokenization entirely. That's a powerful statement, and it shows you just how fundamental and how much of a problem this layer truly is.
Which leaves us with a final thought to chew on. The leap from a forgetful AI to a learning one came from identifying and solving a problem at this hairy layer of tokenization. So it just makes you wonder, what other fundamental messy layers are we overlooking right now? What's the next hidden problem that, if we solve it, could unlock the next major breakthrough in AI?